Thank you for the opportunity to speak. I would like to share with you an idea we have been exploring, and that focuses on testing a hypothesis about laser beacons, and especially interstellar laser beacons, and an idea that we think may be testable now with emerging technologies in new ways. So this is work we have been doing with Chalung Lin, Tom Milster, Kevin Wagner, and Pete Warden from the University of Arizona. So why optical beacons? And of course, there are many ways to think about the search for especially interstellar signals from other civilizations. I think there's two perspectives I wanted to bring in here in particular. One is that the communication ultimately is always basically involving two partners, and it has a goal. The sender's goal, we can presume, is to ultimately influence somehow the receiver's behavior. So there's an intended action that has to emerge from the transmission of information. Now, another angle I would like to bring in here is that I think it is safe to assume that because interstellar communication is not easy, the cost may not be negligible. So if that means, and there have been, of course, studies arguing for this, that we, in terms of assessing potential ways of communicating, we have to consider the costs for the sender as well as also for the receiver. On the left-hand side, I just checking if there's any messages. Okay, so in terms of probability of success, I think it's interesting to consider basically that a sequence of steps has to successfully occur for the communication to be successful. So first of all, the signal has to be detected. And that is, as we will discuss, it's really non-trivial. We all know that. Then it not only detection in itself is not enough. The signal has to be identified as a signal, as a carrier of information, and then it has to be interpreted correctly. And finally, it has to lead to the intended action by the sender. Probably from the sender's perspective, that is the criteria for success. I would make the case, and it's probably most of you will agree, that probability, the combined probability here is not fully, but in large ways, is driven by the probability of detection. So the probability of detection is not necessarily high, and that is because the sender and the receiver have to meet in a complex parameter space. So a high-dimensional parameter space, time, of course, not just the time when the message is sent, but also the cadence, and then, of course, depending on the carrier, frequency, polarization, etc. So it's a high-dimensional parameter space. It's in the sender's interest to maximize, in other words, maximize the success of detection, to increase the probability of success, and then also drive down the cost. In terms of attempting communication, another perspective that has been argued for, and which I agree with, is that interstellar communication, because of its challenges, it's probably a long-term endeavor. These are projects that probably may be lasting centuries or millennia. And if that's the case, the cost is both, if you like, CapEx and OpEx. So it's both recurring costs and non-recurring costs. So non-recurring costs could be building a facility, but for a long-term project, recurring costs may be much more significant than actually the initial capital expenditures. And that all of this is to say that it does matter how much does it cost and how efficiently can a project be sustained over long time scales. So Benford et al. And Shostak and others have argued for this, that we should consider what is the cost of basically sustained operation. By combining these two, I think there is a clear incentive for the sender to maximize the detection and the ability to localize the source of the emission while minimizing the long-term transmission costs. So that's basically an argument for why beacons may be a useful and important component. They can help with signal localization. And if you basically can cut down the parameter space in the first 4 or 5 dimensions, then it makes the search much easier. So it does mean that it lowers the cost also to the sender, because they can be more confident that their message is found. So with the beacon, you can, of course, mark spatial temporal position of the signal, and multispectral beacons will likely increase the chance of success. The more wavelengths your beacon can operate, the more likely it is that it will be found. So efficient beacons, that is basically executed at low cost, operational at low cost, and easy to detect. They can be a significant booster for the success probability for communication. That's, of course, one of the reasons why lasers have been identified very early on as an interesting option for beacons and communication in general. Lasers can operate at a variety of wavelengths, but they can be, of course, operating at wavelengths close to the stellar blackbody peaks, which are presumably commonly detectable for civilization. So the emission technology itself is not very challenging. Lasers were invented relatively shortly after radio telescopes. Within 1 year of the invention of lasers, it has been proposed that they are also well suited for interstellar messaging by Schwartz and Towns. And studies by Shostak, Benford et al., based on similar arguments I made earlier in this talk, that consider the cost to the sender, together with the success of the communication, also argue that brief targeted laser pulses are likely the cost-optimal channel of communication for sender and receiver. So, of course, with light waves being shorter, the equipment required for positional targeting, sending, receiver can be more compact than if one is using much longer waves. So there are advantages. Of course, there are some challenges. The stars themselves are bright, so they provide a significant background. The common way around this has been to suggest that laser pulses can be compressed to such a short duration that they pack a lot of very high energy density. And so for a very brief period of a second, a very brief fraction of a second, you can outshine your host star. So this could be a nanosecond, but modern laser systems actually are exploring the attosecond range, so well below even femtosecond. And so that is true. Of course, what also happens is that these ultra-short laser pulse systems are very highly complex systems. They are usually based on optical parametric oscillators. You basically have to decouple the light, amplify different wavelength ranges separately in a nonlinear amplifier, then combine them back again, compress your pulses. So I note here, and that will be significant later, is that the costs of basically creating shorter and shorter pulses go up very sharply, even with modern technology, while you can buy laser diodes that can be operated at a kilohertz rate and sampling milliseconds, basically, for a few dollars, or in bulk, probably less than $1. Nanoseconds, you could reach by a few tens of dollars to $100 diode. If you actually want to build femtosecond or attosecond laser systems, those will go into tens of thousands to many millions of dollars. So there is a cost implication of what is used. And it's not just cost, this really signifies complexity of the system. If I think about deploying, say, a transmission system that has to operate for centuries, with preferably fully automated without much interference, I would probably opt to go with relatively simple systems that are more robust and don't require continuous tuning, such as the ultra-short laser systems. Of course, it has been identified that there's a promise to using laser pulses for communication. So there have been many exciting optical SETI programs over the past 25 years and probably even longer. Most of these, not all of them, but many of these have been targeted searches, targeting star by star individual sources, and often looking for either ultra narrowband emission that could be basically monochromatic emission from lasers or very short laser pulses, usually typically using avalanche photodiodes, which have the ability to basically detect nanosecond duration pulses. There's one particularly exciting concept that's relevant for what I'm discussing here. It's a UCSD-led concept. Shelley Wright has been leading it. I'm not sure of the exact state of the project now, but I know that there was a successful proof of concept demonstration in 2019 and 2020, and they showed that a Fresnel lens-based system, so this is a refractive Fresnel lens, which is a non-continuous surface lens, can basically collect light, focus it onto an avalanche photodiode array. This is an actual small array of 32 by 32 pixels in the full concept. And with that, they would be able to detect nanosecond pulses. So this is an exciting concept. I'm not sure that it's moving beyond the conceptual design and proof of concept state, but maybe some of you do. I think the two major limiting factors with this technology is that the Fresnel lenses used here, these are acrylic lenses, while they have many advantages of being light and mass producible, they provide very limited image quality. So that matches with the fact that the photodiodes are also covering very large chunks of the sky, but it does combine into basically very, very limited spatial resolution, and then also may increase confusion with background sources. And with this design, it's very difficult to improve on this significantly. So in this presentation, we are arguing that actually we should also be considering beacons not just inside planetary systems, but outside planetary systems. So actually moving an automated laser beacon system transmitter outside a planetary system can have significant advantages, especially by lowering the background. So by moving farther away from the star, the beacon becomes spatially resolvable from the star, and that basically means many, many, many orders of magnitude decrease in the background the beacon has to compete with. So this is quite probably possible for long-term projects and maybe the optimal solution. That does mean that we actually could, or these beacons could be operated with much simpler technology. You don't need to use nanosecond or femtosecond or attosecond pulses, but you could go with much longer duration pulses, millisecond or microsecond pulses that are easier to emit and maybe easier to detect, and then also require much less fine-tuning than the sources. They are also less sensitive to interstellar extinction, broadening the pulses. So a hypothesis that we are thinking about, we are exploring, is that there are detectable millisecond, microsecond interstellar beacons operating in the visible or short-wave near-infrared in the local galactic neighborhood. These beacons may be present and we may not be able to detect them in current data because the integration times are long enough that we collect always too much background when we are observing these locations. They may also not be centered on stars, and that means that we targeted searches may be missing them. Now, they are not necessarily easy to find, but there are emerging new technologies that can help. So we are arguing that if we could move from single source or very low resolution to high spatial resolution searches, we could realize 100 million times efficiency gain by basically using massively parallel searches with the arrays. The three new technologies that are emerging that were not previously available is really at-scale data processing. We are now at the time when we can process millisecond, maybe even microsecond data, even for larger images, and find relatively simple differences. We also have two other important technologies. There is rapid readout imaging detector technology. CMOS detectors have been making a lot of progress, specifically the Q-CMOS detectors, which now allow less than an electron readout signal readout noise levels that basically operated at kilohertz rate. So these are new devices from Hamamatsu, but others are also making progress on that. And then the technology that my group has been working on are low-cost, extremely large field of view telescopes. I will show a couple of slides on that. And really the combination of these three, I think, opens exciting opportunities that I will mention briefly. So our mode lens technology, mode stands for multi-order diffractive engineered surface lenses. Our goal has been to try to provide a technological alternative to telescope mirrors, which have been, of course, at the heart of most astronomical telescopes, but they take a long time to fabricate, they are expensive, and actually they are very expensive to operate in terms of the downstream requirements that your space telescope or ground-based telescope has to meet. So our goal has been to drive down the costs of space telescope by mass producing large optics, similarly to how you mass produce car windshields. So this is basically glass molding, which is an independently matured, commercially available technology. We have built a succession of prototypes, raised over $7 million, advanced this technology from an idea to actually thermally, vibrationally, and vacuum tested equipment. And we are currently working on a space demonstrator to launch before the end of next year. And we have a capability coming up to mass produce lenses that are 1 meter plus in diameter. To be clear, these lenses are producing very high image quality, so near diffraction limited performance over very broad wavelength ranges. This is one example. These are flat lenses where the focusing is done by a complex diffraction pattern, and they can remain flat even if you scale them up. So these some images from our labs, integration of the system, and then operation on a mountain outside Tucson. We are primarily working on this to enable much more ambitious space telescopes. You see some renderings here of developing large 4.5 meter diameter units that make use of this new optical telescope technology to enable low-cost mass producibility. I will not go into details here, but if you are interested, please look out for the Nautilus Space Observatory concept. The key point for this presentation is that this optical technology not just enables low-cost space telescopes, but it also enables lower-cost, efficient ground-based optics. So they are, in addition to the ability that we are able to mass produce these with molding times that can be just less than a day for large optics even, they are also much less sensitive to misalignments, so it's easier to work with. That means cheaper systems, and they can also be designed, lens-based systems can generally provide much larger field of view. So they are actually very well suited for this specific project too. They can provide low-cost, lightweight, compact, and rapidly fabricated telescope systems. So we believe that this technology could also have really interesting implications for testing the hypothesis that there are laser beacons out there. It would also be, from an astrophysical standpoint, very compelling to execute a project where we scan the entire sky for sources, time varying sources of a millisecond to a microsecond range. These could be laser beacons. They could also be astrophysically interesting sources. We envision a project where we could complete this scan in 10 years, monitor each field for about a week. This is just a concept currently, an idea we are exploring. We envision a ground-based realization of this because it's much more efficient here. A mode lens-based solution would ultrawide field of view, high image quality, probably a northern and southern station to allow full sky coverage, and realize basically this survey with 4 telescopes, each of which about 1 meter diameter, designed to provide ultrawide field of view, and then match those with maybe the Q CMOS detectors that I've shown, or there's next-gen detectors that will allow it to run at even higher rates. So this would be exciting, I think, for testing the hypothesis of light beacons being detectable in the solar neighborhood, in the galactic neighborhood, but also for broader astrophysics. So I will stop there, and I will be happy to take any questions. Thank you.
Perfect. Thank you so much for excellent talk and being on time. We have a couple of questions. You can see them in Q&A box. I can read out. What other science would be made possible? You mentioned that it could be broad scale, yes? Just mention a few people. David Clemens suggested astroseismology or planetary transits or else.
Oh yeah, so planetary transits, but I think really basically this kind of millisecond transients is not well explored. So I think there are certainly some stellar activity that we could be studying. Pulsar light curves have been mentioned. Certainly, if it's an atmospheric system, we may have the ability to also look at atmospheric transients. So these are just a few, but there could be also benefits for in some high signal-to-noise ratio situations for even studying things like asteroids, basically nearby asteroids at a much higher time resolution.
Yeah, it seems like you have to start it, and then you will see. There's a lot of things to do.
There's certainly a discovery space in this too, yes. Mm-hmm.
All right, thanks. Next question from Chris Lintott about Argus array. Are you familiar with it?
Yes, yeah, somewhat, yes. I'm not involved. I think that's a very, in many ways, very complementary concept. And I'm not involved, so I don't know exactly what is their shortest integration time, but I don't believe that they go below a second. So this basically would require the dedicated detectors and also much larger diameters. Their telescopes, I believe, are 40 centimeter. I think they are 40 centimeter diameter telescopes. So what we envision here would have larger collecting power, and it would be designed basically for much shorter pulses. But there could be a closer synergy with that Argus system, I think, than I described. So maybe there are more overlaps. Mm-hmm.
Okay, so there is another question which was written in Spanish. Try to translate it. It's kind of, is it possible to repair and exchange? How much it costs? It's my free space translation.
How much it costs, and what was the other?
If it's possible to repair or
Yes. So basically, just to distinguish, basically the Nautilus concept I briefly showed, that's in space, and that's a very large space telescope, very expensive. What we envision here would be a ground-based telescope that would be very easy to repair, and it, in fact, is basically designed to be a simple telescope system. I don't have yet really cost estimates for this, but this would be something that would be probably in the 10, 20, $30 million range, and not hundreds of millions like would be typical for a space telescope.
Okay. The question was, is it worth to repair or replace? Yes, that was about the cost.
Oh, that is interesting. I think on the ground repairs are relatively easy. So I think on the ground it would make sense usually to replace components. The optics is our goal is to really produce it quickly and cheaply. So one could envision, for example, not just replacing the optics, but you could replace the optics not to repair, but to actually change the capabilities. What is the field of view or the wavelength range of operation? So you could upgrade it if you like.